think we can get started. So yeah, hello everyone. Today we have Christian Aganze, who is a graduate student at UCSD and will be moving to Stanford as a postdoc this fall. And Christian will be talking about detecting gaps in globular cluster streams with Roman telescope.
Hello, thank you for having me here. As you said, my name is Christian Aganze. I am a grad student at UC San Diego. And today I'm going to be talking about a project that I'm working with Sarah Peterson mostly and Jessica Zuckerberg on finding gaps in streams with the Roman telescope. It's going to be a short talk. So first of all, we know that simulations, they predict different type of dark matter they can assume. So in cold dark matter models, you have more structure around like the new compared to one dark matter models. So here I'm showing some pictures from the Bullock and Yanko King review paper, where they're looking at a Milky Way size halo and looking at all the substructure on it. This is mostly dark matter only simulations. And most of these models agree on a larger scale, and we want to see what happens on a smaller scale. So we have some observational probes for that. Some of those are dwarf galaxies, or looking at lensing, or looking at stellar streams. With dwarf galaxies, we will have to actually image the halo, and this requires that it's actually not a dark halo. And we can also look for dark halos by doing like lensing and stellar streams. So this is really one way to actually probe small scales and constrain the mass function, the subhalo mass function that comes out of these simulations. So my talk is going to mostly focus on stellar streams. Just a little bit of introduction what they are. I'm going to show a really nice cartoon that I took from Adrian Price-Whelan. This is just a cartoon version of what a stellar stream is. So stellar streams are these tidal features that form in galaxies when you have like a globular cluster or satellite galaxy that's being disrupted. So in this case, I'm showing on x-axis just an x coordinates versus the y coordinates of a stellar stream in the Milky Way potential. So they have like a nice disk and a bulge. And this is the orbit of the globe of the cluster. And then as it orbits in this potential, get disrupted. So you have like a leading arm and a trailing arm in red versus blue. And this image here is showing the same, basically, cartoon version of the simulation, but it's being centered around the cluster instead. So we know of these structures. We know that they exist in the Milky Way. For instance, here is the compilation of all these streams. At least we know at least about 100 in the Milky Way, from satellites and from globular clusters. So this is compiled by Matteo in 2023. It's called the GAP streams paper. You will find it. So the color scheme here doesn't really mean anything. It's just a qualitative thing, but they are showing all these streams. One of the big one is the Sagittarius stream, which kind of goes through center. These streams are really powerful probes for dark matter substructure because, as Gaia has shown, they have these gaps in them, and these gaps can be caused by the interaction with dark matter subhalos. So this image here, this picture here is taken from Bonassa 2019. These are Gaia data. So this is the GD1 stream. On the x-axis, it's an angle along the stream, so the gray circle that's at the stream, and then same thing for the y-axis, so phi1 versus phi2. The top panel here is an observed track of the stream, and then the bottom panel here is a reproduced simulation of the stream. And mostly in this paper, they were trying to reproduce the structure that you see here, which is the gap. And they were able to constrain that this probably happens around 500 million years ago. And it was caused by a subhalo of 5 10 to the 6 solar mass. That's a little bit compact, so that is a radius of 10 parsec. And at an impact parameter of 15 parsec. And then this is probably where the progenitor of the stream used to be. And again, these are all proper motion selected sources that are in GD1. So there's also, yeah, sorry, go ahead.
Maybe I missed it.
Yeah, so we are the stream, and then we're just looking along the great circle. So the great circle meaning this, if you take a plane and the intersection of the sphere, so this would be phi1 versus phi2.
So -40, where is 0?
Sorry?
In -40, where would 0 be?
I don't quite know exactly where they start. It's a cylindrical, it's a two angles. So yeah, I don't quite know exactly the convention. Yeah.
Slides over there.
So 0 is really not the center of the stream. So it has to be somewhere here, but I don't know exactly. Maybe it's the beginning of the stream, but it's definitely not the center of the stream. So the center will be here, and then you can keep going, but there's nothing interesting on this side of the stream.
Can you explain what the progenitor means?
So yeah, the progenitor. The progenitor is if I go back to our cartoon here, when the stream is forming, it's forming either from a cluster or from a satellite galaxy. And this progenitor just means this, because eventually all the stars will get kicked out of the
in the center.
The center.
Before it gets stretched out.
Yeah, so it becomes like a gap. This is what I think, at least for this stream. So we know at least this is true for GD1, and then there's another stream called Panama 5 that people have tried to also look at under density in the stream. Most of these are really under density and weird looking features. So we want to increase the sample size of this, for instance, by looking at external galaxies, because the Milky Way only has 100, so we want to see more. So people have tried to look at this type of features around other galaxies. This is an integrated line, so it's not really with all stars, but this is from the Martinez Delgado Celestium Legacy Survey, where they're just imaging all these different streams to try to see all these galaxies, to try to see tidal features in their halos. Most of these are really probably dwarf galaxies that were being disrupted. But we expect that Roman and Euclid and national surveys will actually find a lot of these. There are no confirmed globular clusters in streams in other galaxies yet. This is a search that Pearson and all tried to do. They're trying to look for tidal features in M31 and M33. This is center of Andromeda here. We have the giant stream. On the x-axis, just Radha's mentioned definition. And this is from the pandas data. This is a survey that has been going on since maybe 2009, maybe before that, maybe 2007. And this is using the Canada French Hawaii telescope. So every feature here is a detection, and at least in yellow. And then there's some artifacts. So the way they did is they're just looking for any linear features, basically, that are over some signal to noise, using some algorithm called the Hopf transform, which kind of try and find transforms linear features into circle in a new coordinate system. So they couldn't find any. They found some globular cluster streams, but sorry, they found some satellite galaxy streams, but they couldn't find any new globular cluster streams or any globular cluster streams actually. But in their previous paper, which 2019, they predicted that Roman will actually be able to do this in resolved stars, because we have this large field of view. And so they're saying that in 1 hour exposure, you should be able to detect these tidal features in the halo of M31. So the first picture here is the stellar density map. So they're just looking at the densities of stars. It's not really an image. Here we're looking at 15 kpc from the center of Andromeda. This is 35 kpc, this is 65 kpc. And this is all for assuming like roughly 1 hour exposure. So the first stream here is like a 50,000 solar mass stream. This is like 5 times that, 10 times that. And this is mostly like a polymorphized in the Milky Way. So we should be able to see these streams in Andromeda. The question that I was trying to answer in this paper is whether we can actually see gaps in them above, well, just with one exposure or above. So to do that, we're just going to make a gap and then try to observe it and see if we can actually detect it. So to do that, I use this code by Adrian Price-Whelan called Gala. So we integrate a stream, starting with polymer 5 as an example, in a potential that's like M31. So we have it's a Milky Way, so it's a M31 potential that's like a disk in the halo. So let me go through the figure and show and say what I'm showing. This is the first panel here, just the stream that's being integrated. Here we're showing a really massive subhalo because just for effects, I usually use a smaller subhalo. This is like a 10 to the 8 solar mass subhalo that goes through a stream and kind of splits it apart. But in this study, we just want to create a gap and see if we can observe it. So we don't actually use these massive subhalos. But the effect, basically the impact velocity on the stars in the stream depends on the subhalo mass. So if you have a larger subhalo, you get more disruption, which makes sense. And then the relative velocity between the stream and the subhalo. Not just the velocity, but the actual relative velocities. And then the scalar radius of the subhalo, if the subhalo is so compact, you get more disruption. And there's so many other factors that you can look in other papers. They explore this in numerical simulations and analytical work. So that's not the purpose of this. The purpose was just to create a gap and see if we can observe it. So this is for a massive subhalo, but we did like a much smaller subhalos. So this will be the result of an unperturbed stream. So this is just a polymer 5 stream. And then if we use a 10 to 10 to the 6 solar mass subhalo, maybe there's a gap, maybe there isn't. Yeah. And then 5 10 to the 6, and then 10 to 1 10 to the 7 solar mass. The reason we care about these mass ranges is because that's where different dark matter models predict different subhalo number counts. So warm dark matter models would predict fewer in this range. So this is all running inside a potential. Again, that's like M31. So we have like an NFW halo bulge in the disk. And here I'm showing that the same data visualized, just number density as a function of x axis instead of x and y. And a larger subhalo is supposed to get a larger gap, and the smaller subhalo get a smaller gap. So once you create a gap in the stream, we just have to just put that in an observational observation. So we have to create like a background stars in M31. So to do that, we sample some isochrones. So here I'm showing some of those assumptions that we use in this study. So we're saying that we're going to observe M31. There are going to be some nuclear foregrounds, and we model those based on just some parsec isochrone and typical elements like Krupa. And then we use some density law for this for the stars, like from Jurith, and also meaning that the disk is an exponential. We have also a halo that's like a spherical halo. And then for M31, we do the same thing, but we put this at 7 at the distance of M31, which is 770 kpc. And then we also model the stellar halo in M31. And here we're only using R and Z filters. But you can imagine if you have more color information, probably do better separation between Milky Way contaminants and M31 stars. So what I'm showing here is a color magnitude plot. So R minus Z versus Z. This will be the M31 stars mostly, and this will be the Milky Way contaminants. You can imagine that you can select those out if you just want to look at the stream in M31. For 1 hour exposure, I'm showing like limits on the CMD that's like 28.9 magnitude. Sorry, 28.7. And then we scale this number to what we observe in pandas. So pandas has observed them for a while, so we just look at what that looks like. But however, pandas looked in I and G, so we just scale that correctly. So let me walk through this plot here. So this is another CMD plot, but this is in G minus I versus I. This is the data from pandas in the South simulations. And then the color code is the number of stars. And then each one of these rectangle is where we scale the total number that we put in the image. So the reason we scale, so this plus circle, no, it's not a circle, this is rectangle, solid rectangle is where we scale the total number of stars in the image versus the Milky Way foreground. The reason we don't really scale to M31 stars is the completeness limit of pandas really drops out when you get to like 23 or 24 magnitudes. So we just scale the total number of stars, and then we put that into not an image, but like a number count map, basically. So this is what I'm going to walk you through. So the first set of panels are those stellar density maps for like 1,000-second exposure versus 1 hour exposure. This is using gaps from like 5 million solar mass. And then we are showing here, this is 15 kpc Andromeda, and then 35, and then 55 kpc. And then this is showing where you're supposed to see the gap. I don't know if you can see it. And the number of stars are resampled in the stream to match the actual isochron of Palomar 5. So in this case, we're assuming some metal poor globular cluster like -1 or -1.5, I believe. And then we are just scaling the numbers correctly. We have some information about how many stars we're expecting, like Palomar 5 in the Milky Way. So maybe you can see this by eye, maybe you can't. And then we wanted to do this if you move to further distances. So let's say, instead of just M31, can we do this in other galaxies? However, we didn't have data for other galaxies. So we just took M31 and just moved it to other distances. This is kind of what I'm showing here. So if you took M31, again, the color, basically the alpha in the plots is not the same as what I was showing before, but this is progressively increasing in distance. And then here I'm showing only for 1 hour exposure. So this is for 8 megaparsec, 1 megaparsec, 1.5, and so forth. So if you just take the halo of M31 and you just move it to other distances. And this here just showing the 5 arc limit line because I didn't want to show a full field of view. So we can also look at the streams at 35 kpc. These streams are thicker because they are at the larger galactocentric radius. And then, it's probably, you can probably see this within 1 megaparsec, but it's really hard to see otherwise. Same thing here for the 55 megaparsec, 55 kpc. And then the other caveat for these simulations is that we are actually making a cut in the numbers. We're only looking at metal poor stars because if we're looking for metal poor streams, then we should just only look at anything that's below -1. But if we actually add all the stars, that really mostly cuts out a lot of Milky Way stars. But if you add all the stars, it's actually even more difficult to see them by eye. So we wanted to see if we can do this just better than saying, okay, can we see this by eye? So we use the gap detection tool. And this is a tool that's developed by Gaby Contardo, 2021. So this tool is mostly not designed for finding gaps in streams. It's just a general tool that can find any gaps in multidimensional data. And the way this tool works is you have a density. So in this case, we have like a 2D image, and you can estimate the density using some kind of density estimator, which is what I'm going to show you here. Normalize, and you can estimate about like edge effects, but you can basically do a density estimation, and then you can do that on a grid, and then you can take, they have this gap statistic, which is at each point in the density map, you can compute the Hessian, so the second derivative of the density, And then if you look at the maximum eigenvalue of that matrix, you will get like a gap. And then otherwise, so that's another density. If you look at the minimum, you look at the overdensities, which will be the stream or anything that's overdense in the map. And this that works in 2D, works in 3D, works in any dimensions. But in this case, for us, it was just like a 2D thing that you can apply. So I call this gap statistic, but it's really that a metric is looking at the Hessian and taking the maximum eigenvalue. So you can locate the gap. So in this simulation, I put the gap at the center by design, but you can try to put it somewhere else and see if you find it. It actually does a pretty good job. And you can also find the stream. So in this case, we are, I'm showing the minimum eigenvalues instead. So that kind of find that linear feature. I don't quite understand all the blobs things that happens, but we actually, we took care of this by actually looking at a grid that's much smaller than the data sets. It's actually the edges. That's how you compute the density. These are the corners. So then we can just fit that to a second degree polynomial and say, okay, we just want to know what the location of the gap is. In this case, so the setup here is we know where the gap is, and we're trying to see if we can find it as we move to larger distances. In principle, if you have observations, you have to find a stream using a stream finding code, like many have been developed. But then you have to look into the stream, look at the fluctuations in density to actually be able to say whether we find a gap there and if that gap is significant at all. So what I'm showing here is we take like the top percentile of the stream stars. So sorry, the bottom percentile of the minimum eigenvalue. So that will give you the stream. And then if you take the top percentile of the maximum eigenvalue, you get the gap. And in this case, we just want to see the location is consistently at the center. And here I'm showing this size here because we actually measure the gap size from looking at the density along the stream before we actually made a simulation. So obviously, any density estimation will depend on what you assume for the bandwidth. So the bandwidth parameter is really just how you do a density estimation. So you have a bandwidth and you have a grid, and you can either use a Gaussian or you can use any other way of estimating densities. You can use that. In this case, in this code, they're using actually some kind of polynomial model. But what I'm showing here is that you can choose a good bandwidth to actually give you consistently the gap at the center. So if you look at the distance of the stream versus bandwidth, only if this blue region means here that you're actually getting this metric that we defined was like the spread of the location of the gap stars. So what this means is that if these blue points are spread out throughout the image, that means it's found gaps everywhere. And that's not definitely a good metric. But if they are concentrated, it means they actually just found it at the center. So that's what these two metrics are trying to track. Eventually, we decided in this experiment that the bandwidth between 0.5 and 1 seemed to be optimal in doing this kind of density estimation. And then that will actually vary. Maybe in real life, if you have an image, you probably want to try a bunch of bandwidths. And then it's still going to be hard to decide actually what's the real gap or not. It has to be inside the stream, obviously. It can be a gap in the background. But then you actually have to measure the density inside that gap and see if it's actually lower than the density in the stream. But for this case, we just looked at the location of these blue points of gas stars. So we call these gas stars. And we just look at basically the median deviation from the center because we put the gap at the center. So this is plotted as a function of distance of the galaxy. So we take the galaxy, we do the trying to find the location of the gap in that galaxy, and then we keep moving the galaxy at larger distances. We see if we keep consistently finding that gap at the center. So this is what I'm plotting here. On the x-axis is the distance of the galaxy and how far the gap is from the center because we put the gap at the center. And it looks like around 2 or 3 megaparsec, we start to lose it. And then we can also do the same thing for, in this case, I'm showing just two different exposures. So one 1 hour versus 1,000 seconds, and at 15 kpc, at 35 kpc, and 55 kpc from the center of Andromeda. So we have Andromeda, different distances Andromeda, and we're actually moving the galaxy as well. The conclusion from this is that we can actually probably detect these gaps within 2 or 3 megaparsec. We definitely would detect them in Andromeda, but we should be able to detect them within the 2 megaparsec volume. So the question is then, how do you do inference? What do you say then about dark matter once you find these gaps? There are multiple ways that people have tried to do this before. For instance, in GD1, in Palomar 5, people have tried to look at the power density fluctuations in the stream. So you look at it, the stream, and then you say, if I include more dark matter or less dark matter, do actually reproduce the density that you see inside the stream, and the gaps and so forth. So that includes, you start from the beginning, you have to have a self-contained simulation. That's the same kind of thing they do. Instead of just looking at power density, in simulation-based inference, instead of just looking at the power density fluctuation, you're looking at everything. You're trying to reproduce just the entire stream track. And so in this case, that's what I'm showing. I'm showing like an image from Herman's 2021, where they just looked at GD1. That's the stream that I showed you at the beginning. Just from that gap itself, you can actually infer the particle mass for warm dark matter models. So in this case, they're showing the particle mass versus the stream age in gigayear. They also had some other parameters, but in this case, they're just showing two. With just one observation of the stream, you should be able to constrain at least, have some good constraints. And if you have 1,000 observables, so if you have 1,000 streams and you find 1,000 gaps in them, you should be able to constrain definitely the particle mass of dark matter. Again, this is starting from the beginning. So you start with the simulation that includes a lot of parameters, and then you try to reproduce either the density or the track or both in some kind of statistical way. So this seems like a promising way to do this, but there are many other things that can cause gaps in streams. So for instance, if the stream is closer to a spiral arm or GMC or Galactic, if it's closer to a bar, you can induce some resonances in the stream that kind of either create a gap or splits it apart. So if you look for streams that are outside in the halo of the galaxy, it's less likely that the gap that you're seeing is probably caused by something like a GMC or from the spiral arms. However, it's still difficult to actually go from, I observe the gap in the stream and I'm saying something about dark matter. But once we have, again, samples of this with Roman, Ruby, and Euclid, we should probably be able to distinguish between different dark matter models. So I'm going to leave you my summary. I don't want to take too much time. So in this experiment, we're trying to see if we can detect gaps in globular cluster streams with Roman. So we started with globular cluster streams that are like Palomar 5, so 50,000 solar mass. We use M31 as the halo of M31 as a test. So we use pandas data. We simulated observations and we looked at the stellar density maps. And then we think we can visually detect, at least in Andromeda, we can detect gaps from anything that's like 510 to the 6 solar masses. That's good because that's where different dark matter models predict different numbers of subhalos. And then if we move to larger distances, maybe we can see this within 2 or 3 megaparsec. And that's around 200 galaxies in this volume, mostly dwarf galaxies, but this could be potentially constraining once you actually have the samples. Yeah, that's it. Thank you so much.
Do the models include any hunting for reddening, which might be important for M31, but if you get these other galaxies, use the internal. Initially, it's Milky Way, right? But is reddening a factor in any of this, or stars are long enough?
Yeah, so we didn't put reddening.
Sorry, could someone repeat the question? It wasn't audible.
Yes, so the question whether we consider the effects of reddening in these bands that we're using, R and Z. And the answer is no, we didn't actually include reddening in our simulations. I think we looked at some of the predictions, at least we looked at the HST data, and there didn't seem to be a lot of reddening. But for pandas, we looked at, actually, they had a reddening model. So this G0, I0 are the rendered data, actually. So we scaled to data that's the reddening, but we didn't actually add reddening in our predictions. If does that make sense? Yeah.
This was actually the plot of the.
Okay, yeah, so here, this is the reddening. I think there's still some, maybe an accounted extension or something. This looks a little bit not as steep as that, but we use the reddening data. We didn't actually want to do our own reddening correction. We trusted what the pandas data had. Yeah, and then there's some structure that we have to reproduce. I think this is supposed to be some Milky Way halo stars. We have some Milky Way halo stars in the simulation as well, but the entire CMD wasn't reproduced accurately.
So, I don't know, you may, exactly a little bit, but you may have said so in your introduction. So the subhalo, is there still pretty much the theory that proposed the idea, or are there any, actual observations supports, the subhalo with mass of potential, 5 to 7 solar mass? There's such evidence for that?
Yeah. So the question is for people on Zoom, if I understand correctly, is whether there is evidence for there's actually any data that support that the gaps you see in streams could be from subhalos instead of.
Right. I mean, you were searching for it, but there's any other evidence?
Yeah.
Actually there. Yeah.
So in the beginning, I started with this picture from Bonassa and Adrian Praswilan. This is from Gaia. So they looked at this stream called GD1. And they could reproduce this. So the gap you see here could only be reproduced from subhalo encountered, because this stream is actually, the orbit of the stream suggests there's no GMCs or anything that actually disrupted it. So
they ruled out any other, because you could have other arm or another dwarf galaxy hasn't been seen or whatever. Did they rule out any other reason?
They ruled out like GMC, spiral arms, the galactic bar. I think that's what I remember, because of its orbit. It's really up in the halo of the Milky Way. But yeah, that's for this stream. People are trying to look for evidence of fluctuations in other streams like Phoenix and Palomar 5 and other streams in the Milky Way. But the signals, again, are still really low, and they're just trying to rule out everything that's not, less likely to cause these gaps. Basically, in the Bovie papers, they do the same thing for GD1, I believe. They looked at the power density. So basically, they take this density here, and they try to reproduce it using the contribution for everything else. So they account for, if you had like this many, the spiral arms in the Milky Way, the GMCs, everything else, can we add up to this? And then if we also add the subhalo itself, we also, then the cluster itself has also its own potential, the Ika model. All of that does not account for the fluctuation that you see in some of the streams. So they can also claim that some of this could be from like subhalos. Yeah, so I don't know if that answers your question. Yeah, that's one way to do it. But again, having large statistical samples is just what in this paper we're just going after, is there a gap? And then the explanation can be needs more statistical arguments to actually get to the cause of the gap in the stream.
We have a question on Zoom.
Okay.
Carl, go ahead.
Thanks. Yeah, I enjoyed this. Thank you. A couple of comments. These when you're talking about globular clusters, there's not many stars, and most of the signal comes from the blue main sequence and the turnoff. And so I would suggest that, if you ever detected streams, that you would then go back and ask WFIRST or somebody to get very deep images, as deep as you possibly can get, of those streams, so that you can actually get your signal to noise up to reasonable levels. The second thing that I'm concerned about is we're still having problems with this in our own halo, is as you've talked about, ruling out all other possible mass concentrations like globular clusters, dwarf galaxies, GMCs, whatever. And this is going to be much more difficult in M31 or any of the, out to 3 megaparsecs, where your orbit determinations for all other constituents are going to be terrible because you don't have really relative distances.
Yeah.
It's a much easier job in the Milky Way. It's going to be a much tougher job out there. Sorry. So, if you care to comment.
Yeah. Yeah, I agree. It's going to be difficult, definitely, to do this in other galaxies, because you won't have any kinematic information, so you don't really know what's the orbit of the stream. There's some work that Jacob Nibero has been doing on trying to constrain the potential of a galaxy from projected streams. This is only just that's the other way people use streams, trying to constrain potentials of galaxies. And they're able to do that without requiring any motion information. So presumably, if we have large samples, maybe there's a way of getting something about the gaps themselves without actually having any motion information inside the stream. But I agree, it's going to be difficult. But these simulation-based inference techniques that I talked about in the end, which basically simulate everything, sometimes they try to learn the probability using some kind of machine learning. They try to actually put some good constraints because you have so many variables, and but people try to actually use this simulation-based inference framework to do some inference, but it's still really difficult.
Mm-hmm. Thanks.
Do any of these streams have RLI variables, or do you have any distance information?
Which streams? So
all the ones in the Milky Way, I guess.
Yeah.
Great to have that for the Galaxies as well.
That's a good question. Yeah, I don't actually know. So this is for precise distances in these streams. Is that right?
Well, that's one thing you could do with RLI.
Yeah.
Yeah. I'm wondering if there's any distance information.
Yeah. I mean, the GD1 stream is from Gaia, so we have really good parallaxes.
Are there parallaxes to it, or is it just proper motion?
Good question. Yeah, that's a good question. I think it's it's so the stars are selected by proper motions. They're moving with the track of the stream. I don't see why we shouldn't have parallaxes for stars that are in there.
It depends on right there.
Yeah, it's depending on how bright that's right. Yeah.
If I could just comment, the parallaxes are actually pretty much crap at that distance. But RR Lyrays have been used for streams, in particular for the orphan stream around the Milky Way. They turned out to be a tremendous tracer, but of course, that's a dwarf galaxy. Globular clusters, typically have a dozen or so RR Lyrays, so that's going to be really tough to try and trace a stream with RR Lyrae.
Thank you for answering that. Yeah.
More question online? If not, yeah, let's thank Christian again.